I'm on jury duty the week after spring break. As far as I know, I can't get out of it. What does that mean for you? Nothing in a practical sense, other than you may have a guest lecture. So classes will proceed as normal. We'll still have lab. We'll still have all that stuff. Unfortunately, my jury number is around 110, which makes it reasonable that I'll be called later in the week. I've never done it before. Has anybody done jury duty before? They're always guilty. That's how to get out of a trial. Demonstrate that I have deep prejudices in my attitudes. All right. So, other than that, we're going to break new ground somewhat today. A couple things that I do want to point out. This has historically caused a lot of trouble. I went over last class, it was in the lab. But again, the reminder, when we look at an underdamped case, this is a sinusoidally, exponentially decaying sinusoid. It's fairly straightforward to get the period. We all have a good feel for getting the period of that. The thing to recognize is this curve that touches the peaks is the exponential term. And that's again defined by whether we're looking at voltage or current, it doesn't matter. We can just call it an A, e to the minus alpha t. So that curve is defined by that exponential argument. You need 2 points and 2 unknowns. And we did that in last class, so hopefully you have a good feel for it. We saw it in the lab. One thing that bears mentioning, this is oscillating and settling about 0. This is an easy exponential fit. On the other hand, if we have something that has a DC offset, the reasoning is the same. So here's our T, and then here's our DC steady state term. And we have something that climbs up and maybe does this. And this is what you kind of saw with the current. And that's exponentially converging to the DC steady state value instead of 0. We have the same exponential fit. So you still have a curve that does this, and maybe it comes down here or something like that. It doesn't necessarily intersect there, so don't assume that. Depends on the phase. And so you still need 2 curves, but in this case, when we were looking at our 2 points, we have a T1, a T2 that have been point and chug, and then again, a V1 and a V2, V1 and V2 that are associated with those 2 points that you use to find the alpha. Well, in this particular case, with this DC offset, we still have a T1 and a T2, but our V, or I, is the offset here. So it's always relative to our DC steady state term. That's a thing to pay attention to. If you actually just used this voltage here, then you'd have a problem. It's the offset from the DC steady state that you're concerned with. It falls out naturally here. This is our VBC, and this is our V. I don't want to call it V1, but V1 in this case is, I don't call that VA. V1 is VBC minus VA. It's the offset. And so when you go and find the alpha and the beta from experimental data, you have to make sure you include that DC offset term. You could alternatively, of course, use this curve as well. So essentially what's happened is this has just shifted up. We've added a DC term and everything just shifted up or down as the case may be. So that's something to be aware of when you do your calculations for the lab, and pay attention in the exam setting as well. One other thing that was asked in both actually the last 2 labs, you worked with inductors. And so in this lab, arguably, we had something that looks like this. Excuse me. Things that is characteristic of inductors, a true inductor looks like this. So there's the L. and whatever it was for our case, 100 millihenries or something like that. So this was 100 millihenries, but this is our inductor. And in this particular case, this is not trivial. Ideally, that's 0. But if you actually hooked up the inductor to the ohm meter, which you can do, it's a safe thing, this actually is probably around 100 or so. So actually that internal resistance of the inductor is larger than our probe resistance. And together they do have an impact on the circuit. So the circuit you modeled in PSpice was the ideal circuit without that guy. But the characteristic circuit that you implement physically has this resistance, and then we have this other resistance. And so the results are going to be a little bit different. Where they're going to play out is in the attenuation constant. The resonant frequency stays about the same, and it's dominant relative to the attenuation constant in this problem. So beta was comparable for both, but the alpha should have been different. And that's something to observe. So our ideal assumptions were not ideal, or not complete. So things to think about. And this is something that matters a lot, of course. So the way inductors burn power, it's significant in a lot of situations, largely because of the internal resistance. All right. Any questions on anything on the lab, of course, or anything else that we've done? Homework? Everything is good? Okay. So, the final part of Unit 3, or Unit 2, is Laplace. So a Laplace approach to solving these circuits. And I handed out, maybe it's still circulating, here's a very partial list of Laplace transforms. This is something you should have seen in your differential equation class. How many people have not seen Laplace transforms at all? That's very unfortunate. And this was a class you took here. So, and this has been a running battle for too many years. I don't know why the math department has a difficult time standardizing their classes. It's a mystery to me. I'm not going to teach you the Laplace transform, so there's not much, I'm going to touch on there. We're going to use this as a tool. So those of you who haven't used Laplace or feel comfortable with Laplace, I'm happy to go over some of the theory for you if you're so inclined. But what we want is we want to go from the time domain to the Laplace. And so effectively there's some math. We can have some function, f of t, function with respect to time, of course. And for us, that's voltage or current usually. And there's a Laplace equivalent. So you take the Laplace transform, it looks something like this. F of t, that's the mathematical representation. That means take the Laplace transform of this function, and the Laplace transform effectively is 0 to infinity, e to the minus st, f of t dt. And evaluate that. We're not going to do that. You don't have to worry about that. You don't even have to write that down if you're not inclined to. You can save some ink. But that is the mathematical foundation for where all these Laplace transform pairs come from. And so effectively, what does that mean for us? Well, we're just going to write this as a function of s. So we take a function with respect to time, and we have a good feeling for functions with respect to time. We know what velocity is, acceleration, all that stuff, position, in this case for us, voltage and current. And we're going to transform that to the Laplace domain. And the Laplace domain is a function with respect to s. S is a mathematical variable. There's no real physical analog with respect to s. It's just a variable. And it's going to be a mathematical tool that we're going to use. So in a sense, this is our physical representation of what's going on. We did homework 5 with all the differential equations. We can find these expressions. This is a mathematical representation of the equivalent response, but in the S domain. So, Laplace transform pairs. If I zoom in a little bit here, can I zoom in? Zoom in. Oh, I guess I always start off. So, Laplace transform pairs. Things to look at here. Here's a step function. We're very familiar. So, our step function is a term that turns on at t equals 0. The Laplace transform of that is 1 over s. So from a mathematical point of view, that's all we care about. If we have a step function source and we take the Laplace transform, in other words, if we do the math, the Laplace transform of u of t just means 1 over s. And likewise, if we look at the Laplace transform of a constant times u of t, well, the distributive property applies, and that's just a over s. So when we turn on the voltage source, oops, I guess I got a little bit lucky that I'm still on. So when we turn on the voltage source at 5 volts, that would be 5 over s in the Laplace domain. So that's what I'm saying about this being a tool. It's a tool we're going to use. It's unfortunate that perhaps you don't have the theoretical background, and then when you take signals, you will be sad. So you may want to brush up on the Laplace stuff a little bit. We're going to just use it directly. So, how does that help us? Well, if we think about what's going on, right now, what we're doing is we're having an input, some source, the source of t, and we're driving that into a circuit, and then we're getting a differential equation, and from here we're going through all the alpha, omega naught squared stuff, finding the initial conditions, all that stuff that you've just done on homework 5. So essentially this box represents homework 5. And then we're getting a V out of that, V out of t, whatever it is. And again, we looked at capacitance, voltage, inductor current, all those things. The process is equivalent. Well, we know that's fun stuff. We like to do that. But there's another approach. We could take this source, take the Laplace transform of the source, and then we get a V source of x. So just a mathematical equivalent in the s domain. And instead of deriving the differential equation, which I know you enjoy, instead of having to do that, all we have to do here is algebra. So that was homework 5. This is 7th grade. And then we get an output, V out of s, in the s domain, and then eventually we transform that back using the inverse Laplace transform. That means inverse Laplace, ds of out, ds, d out of s. And then we get our time domain response. So we're using this as a tool. Now, I was a little mocking on the algebra. Of course, the algebra does get a little bit messy, but it is still just algebra. It's a bunch of ratios that we'll deal with. So arguably, algebra is easier than differential equations. Most people think so, but actually there's always a few who prefer to do things this way. In higher order methods, this way is easier, though algebra does get a little bit fun periodically. So, what are we looking at here? Well, when we look at a Laplace function, and we'll just do an arbitrary Laplace form, so that's a function in the s domain, what we'll eventually do, or we'll aspire to, is some ratio ns over ds. N being numerator and d being denominator. Ns and d of s are polynomials. So they're just a polynomial. S squared plus s plus 1 or something like that. An arbitrary polynomial right now, but they are a polynomial form. So if we look at this, if this is a polynomial, then the roots of the polynomial, roots of the numerator, are called zeros. And then the roots of the denominator are called poles. Zeros, this is more unit 3. We'll find the zeros, but they won't have any physical significance for us. On the other hand, the poles will have some physical significance for us. These poles specifically will be the e to the st term. They're the s and the e to the st that we used previously. So when we looked at these second order differential equations for the homogeneous term in the natural expression, I used this e to the st guess. We plugged that in, and then we found that there were two solutions, an S1 and an S2. And lo and behold, our denominator polynomial in our functions is going to be poles, and they're going to correspond to whatever the S was that we saw earlier. If we think about this process a little bit, just do a simple example. And this is in the sheet we handed out. F of s is 2s plus 1 over s squared plus 6s plus 8, no, 8, just 8. Oh, 8s, sorry. Let's read it correctly. That's cubed. It's off by an order of magnitude. So, one of the very first things we're going to ask ourselves as we look at these expressions are, what are the poles and zeros? It's on the sheet in front of you if you're having a hard time reading what I wrote. Well, hopefully you agree. Zeros, we find 2s plus 1 equals 0. Find the roots. There's one root. There's a 0 at minus 1/2. Or since the TA doesn't like fractions, minus 0.5. Those of you who ran into that.
Excuse me.
Yeah.
Question, is this S what?
It's the same problem in the handout, but yeah, it's hard to read since I scribbled. S cubed plus 6s squared plus 8s. That's a little bit from there. So we have a 0 at minus 0.5, and the poles, a little quadratic method, or however you want to use. We have a pole at 0, a pole at minus 2, and a pole at minus 4. You can find that in your calculator and verify that. But what does that mean for us? Well, in some sense, if we take this expression, that means we can write f of s equals 2 times s plus 0.5, or 1/2 if you're inclined. S times s plus 2 plus s plus 4. So that's the beauty of finding the poles and zeros. We can find these simplified or parenthetical expressions and write it like this. Now, why do we do this? Why do we care, in some sense? Well, there's a tool in Laplace and other mathematical applications called partial fraction expansion. Anybody not heard of this up here? So we can do partial fraction expansion. And so what does our partial fraction expansion expression give us? Well, that means we can write 2 times s plus 0.5 over s plus 2, s plus 4 equals some a1 over s plus an a2 over s plus 2 plus an a3 over s plus 4. That's the partial fraction expansion. In the denominator of each of these terms, we have our pole. So the first term is the pole equals 0. The second term, pole equals minus 2. Third term, pole equals minus 4. Now, why do we care about that? Well, if we have an expression that looks like this, and eventually we find our zeros and our poles, and we get this in a partial fraction expansion, arguably, I can take the inverse Laplace transform of this, so Laplace minus 1, f of s, equals, of course, the inverse Laplace transform of our original expression, just to write it out, 2s plus 1, s cubed plus 6s squared plus 8s is the inverse Laplace transform of this partial fraction expansion. So just the substitution of all the parts we've done along the way. Why is that useful? Why is this useful? Well, lo and behold, if we go to our table, and I told you we wouldn't have to derive this, we can find various inverse Laplace transforms. We can break this into parts. This is distributive, so we can write this as inverse Laplace transform of a1 over s plus inverse Laplace transform of a2 over s plus 2 plus inverse Laplace transform of a3 over s plus 4. And so, well, if we break that into parts like that, and that's perfectly valid mathematically, what's the inverse Laplace transform of a1 over s? Well, I go find that on my table, and lo and behold, that is my step function. It's hard to read here, of course, but you have it in front of you. So that's just a1 u of t. And what's the inverse Laplace transform of a2 over s plus 2? Well, if you go to the next page, you can see that's an exponential argument. Again, a little bit hard to read online, but that's an exponentially decaying term. So we have plus e to the minus 2t u of t. Everything is for t greater than 0. So I won't always write the u of t's down. We know our solution is for t greater than 0. We've talked about that before. As far as we know, the world starts at t greater than 0. And then here again, it's the same thing. We have an exponential, one with a constant over it, so a3 over s plus 4 in this case, in the inverse Laplace transform of that. Oh, and I left off an a2, of course. a3 e to the minus 4t u of t. And so if I collect my terms, write that a little bit more cleanly, we can write this as a1 plus a2 e to the minus 2t plus a3 e to the minus 4t, and all of that, of course, valid for t greater than 0. As I look at this, it's a little fuzzy. As I look at this, what does that make me think? In terms of circuit, well, what I said, what does this look like in terms of circuits, or in terms of homework 5? Overdamped. It looks like a second overdamped circuit, right? Two real terms, an S1 and an S2, negative and real, and then a DC term. So this looks like a second order circuit with a DC or a step function source that's overdamped. Of course, we don't know what A1, A2, and A3 are, and we'll find those in just a minute. But that's what we want to do. So if we can get a function for our circuit that's characteristic in this form, we can go through this process with the partial fraction expansion. We'll find the coefficients in just a second, take the inverse Laplace transform, and lo and behold, we have our circuit response. So we don't even have to go to the differential equation. That makes us happy, perhaps. So how do we find the A1, A2, and A3? Well, to back up a step, we had S plus 0.5. S plus 2, S plus 4 equals A1 over S. So this is the same thing we've written down already. And so how do we find A1, A2, and A3? We use something called the cover-up rule. Kind of a selling name, but loosely applies. How do we find A1? Find A1. Multiply both sides by S. Which is the denominator of A1. Of the A1 term. And evaluate at the pole. Which is S equals 0. Right? So we evaluate at that pole. So we take this, multiply both sides by S. And so hopefully I agree, you agree, I agree, of course. Hopefully you agree. This winds up being S plus 0.5 over S plus 2, S plus 4 equals A1 plus A2S over S plus 2 plus A3S over S plus 4, all evaluated at S equals 0. Well, what's the nice thing about the cover-up rule? The other terms go to 0. Right? We have that 0 in the numerator, and so we plug in that 0. 0 over something is 0. We learned that back in the day. And then what are we left with? Well, we're left with 1 over 8 equals A1, or again, to make the TA happy, A1 equals 0.125. And that's how we find the coefficients using the cover-up rule. And we can do the same thing for A2. So, for A2, our denominator is S plus 2, so we multiply by S plus 2. Evaluate at minus 2. S equals minus 2. And so in that case, we wind up with 2. And I'm not writing out all the steps, of course. I'm doing some of the algebra fairly quickly. S plus 2 over S plus A2, A3, S plus 2 over S plus 4, all evaluated at S equals minus 2. And once again, I hope we recognize these two terms vanish. You can plug in minus 2 to this expression, and if I did things correctly, we get A2 equals 0.75. And so that's a fairly mechanical process. And we can do the same thing with A3. I don't think you really necessarily want to see it, but A3 you can check later. A3 equals minus 0.875. So, and you don't have to use the cover-up rule perhaps on the exam. You can certainly verify things with calculators. But do show me that you know how to set up the partial fraction expansion and whatnot. So it will be asked for. And so where does that leave us? Well, then our f of s now was 0.125 over s plus 0.75 over s plus 2 minus 0.875 over s plus 4. And hopefully those are all correct. Probably should check. And then what does that mean for us? F of t then equals 0.125 plus 0.75 e to the minus 2t. So now just plugging in the coefficients that we had left as a1, A2 and A3 a minute ago. And that's a minus 0.875 e to the minus 4t. And again, this is all valid for time greater than 0, so we'll throw a step function there at the end. And that would be our perhaps voltage response or current response for this critically damped circuit that we saw. So these are the things we're going to look at. And the trick then is, how do we find f of s? Well, this is a transfer function. A little terminology for you. It's called the transfer function when it's in the form polynomial over polynomial. Again, I said this already, but just to emphasize. And so once we get our relationship between our parameter of interest, capacitor voltage, inductor current, whatever the case may be, we want to get a numerator over denominator, polynomial over polynomial, apply partial fraction expansion. We don't have to worry perhaps that whether it's underdamped, overdamped, or critically damped. We can apply partial fraction expansion to any case using partial fraction expansion rules, and it will naturally give us the damping. So we don't have to know in advance the form of the solution. With that in mind, we did recognize this is critically damped. So critically damped circuit. In this case, our poles are real and negative. And we've already seen that. So that was our S1 and S2 when we analyzed this using differential tools. Our poles are real and negative. Our exponential transients have to decay with time. So there is something called a pole zero plot. And we'll look at these. And so we're going to start looking at imaginary or complex numbers. So we have imaginary and real axes. And so we'll represent poles by O's and zeros by X's. No particular reason. There is a convention here, and I usually forget what it is, so I hope I got lucky. But we have a pole, in this case, for our case that we just looked at. We have a pole at 0, pole 1 at 0, pole 2, at -2, and pole 3. And the numbering of pole 1, pole 2, and pole 3 arbitrary at -4. And then we have a 0 at -1/2, -0.5. And so this is a pole 0 plot. And this is something you'll see quite a bit more of in future classes, but I'm introducing it to you here. There is something to recognize here. So our poles, and in this case are 0, but more importantly, our poles are on the real axis. What does it mean if our poles are on the real axis? And negative. We'll talk about if we have positive poles in just a second. That means we have a critically damped response. So it's just another way of saying the same thing. But this is a plot format. So if our poles are on the real axis, there's no imaginary term in our pole, we have a critically damped response. And so this is the problem we just looked at. F of s, just to write it out, 2s plus 0.5 is factored in here. Same thing. That's that problem. Another thing to make an observation of in this particular plot, we have a pole at 0. What does a pole at 0 imply for us? Do we know? That's a DC term. So if we have a pole at 0, there's your DC term. You know you have a DC term. So if we have, in our partial fraction expansion, if we find a pole at 0 like there was in this problem, there's a DC term. If there's no pole at 0, then there's no DC term. There's no DC state, or it's 0. You have our DC steady state would be 0. Anybody still writing? Yeah.
So when you found the equation, isn't that the form of an overdamped response?
Yeah. Is that not what I was saying?
That,
Sorry. Was I saying critically, Dan?
Yeah.
Wow. Yeah, it's overdamped, of course. Wow. Because we're all ready for spring break. I pause it. Overdamped. Very much overdamped. Exponentially in plain terms, overdamped. Critically damped we'll do next, but that's no excuse. So, don't get old. Bad things happen. Anyway, yes, it's overdamped, of course. Overdamped, very important. Thank you for asking. Or thank you for pointing that out. All right, so. What happens if we have a pole on the real side? So let's say we have a pole here, a pole at +4. And essentially that would correspond to something along the lines of f of s equals, we'll just call it a1 over s minus 4. Right? So that's a pole at +4, that's the root of the denominator. Well, if we think about the Laplace transform of this, inverse Laplace transform of f of s, well, that's just a1 inverse Laplace transform, 1 over s minus 4, and that's still in our Laplace table, which was somewhere. It's still the fraction expression. It doesn't matter what the sign is. It says s plus alpha, but alpha can be a positive or negative number. It doesn't matter what the sign is. And so what do we wind up with? Well, if this is s plus alpha and the Laplace transform is minus alpha, if alpha is negative, then this winds up being a1 e to the s, not s, e to the 4t. It's a 4. E to the 4t. What can we say about this as time goes on? It gets bigger and bigger. So this is an exponentially growing response. As far as systems go, what would we say about this? This is not stable. So this is an unstable response, unstable response, not stable. Exponential growth cannot happen. And so what does that mean for us in terms of our poles? Well, any pole that's going to be positive is going to produce an unstable response. Are our circuits capable of being unstable? Being not stable? Can we have a circuit that's not stable? It's a little bit of a trick question. There is a yes answer. There is a yes answer, but not the answer I was looking for. So if our components are passive, our RLC circuits never are going to be unstable. They're always going to be stable. How could we actually create a circuit that wasn't stable? What would we have to introduce? What would we have to introduce? Dependent source. So we would have to add dependent sources. You can't do the left half of our infinite plane, and this is I am in real, of course. 4 stable responses. Poles must be in the left gap plane. More specifically, the real component of a pole has to be negative. Well, I should say less than or equal to 0. 0 is kind of the special case, and we'll see that in a minute. So it has to be less than or equal to 0. So we cannot have positive poles, that would be bad. So this is a stable region. We have instabilities on the right hand side. So, are we still writing? Well, with that in mind, we looked at real poles. What about a different case study? F of s equals 4s over s squared plus s plus 1. And we can do the same reasoning. We can find our zeros. Hopefully you recognize there's a 0 at 0. And again, we're not going to use the zeros for anything right now. I do want you to recognize they're there, but come unit 3, our zeros will have physical meaning. So for the moment they don't. And then we have a pole minus 0.5 plus j 0.866. And again, I use j. Get used to it. Minus 0.5 minus j. It's supposed to be 6. 0.866. So those are the poles associated with this quadratic denominator. We brought this up once before. What can you say about that pair of poles? Conjugates. They are conjugates. So if we call this P1, we call this P2. P1 is the complex conjugate of P2, or vice versa. Doesn't matter which way you say it. So they are complex conjugates. What does that mean for us? Well, if we go to our pole 0 plot, we have a 0 at 0, we have a pole here, and a pole here. And that's minus 0.5, and that's 0.866, and minus 0.866. And then imaginary and real again. Is this stable? Sure. So the real component of our pole is less than 0, so it's stable. What does the imaginary component do for us? What type of response are we going to get here? Well, if we think about this, we can do partial fraction expansion the same way. So we'll wind up with an f of s equals a1 over s plus 0.5 minus j 0.866 plus a2 s plus 0.5 plus j 0.866. What's the inverse Laplace transform of these? Do we know how to take the inverse Laplace transform? It's the same. It's still an exponential. So this is the fraction. Nothing's changed. This is still this guy. Alpha is now a complex number. No big deal. Complex numbers are still a number. I was going to say a real number, but that would be stupid. Complex number is a number, a valid number. So this winds up being the inverse Laplace transform of f of s, just winds up being a1 e to the minus 0.5 minus, there's a j in there, 0.866 t plus a2 e to the minus 0.5 plus j 0.866 t. Right? So we can still take the inverse Laplace transform, and this looks familiar. We didn't actually solve it in this form, but what type of a response is this? It is sinusoidal, but more specifically, it's an underdamped case. Underdamped. And so, in our I am real plot, underdamped cases will have a complex conjugate pair. Pair of poles. And that implies underdamped, as we just said. And so we will always have two poles when we're underdamped for second order circuits, of course, more for higher order circuits. But we'll always have two pairs of poles when we're underdamped, and they will be complex conjugates. Does this term have a DC steady state? Well, it's zero. Because technically it does, but no DC term here. We could have a DC steady state term, so we could have a real pole here as well. We'll have to replace that zero, of course. Looking at this, that's alpha, that's beta. So coming straight out of the roots of our polynomial, we can find alpha and beta directly. And we saw that a bit when we looked at the differential expression as well. How do I find A1 and A2? How do I find A1 and A2? The same way. So we still use the cover-up rule. And we can find A1 by multiplying by this long expression. So we wind up with, what was our numerator? 4s over s plus 0.5 minus j 0.866. Yes, you could have waited. It's all right, I would have taken it. And so we can see it actually gets a little bit messy to write out just because it's long, but everything still applies. So what do we do to find A1? Multiply by the denominator. So we wind up with that going away, that going away, that going to 0. And then we evaluate at s equals minus 0.5 plus j equals 0.866. And this is where having a calculator that does complex numbers does come in handy. I recommend you familiarize yourself with your calculator if you haven't used complex numbers on it before. On the same token, if you don't have a calculator that does complex numbers, it will certainly make your life easier in the exam if you get one. So I hate to tell you to go spend more money, but it's probably money well spent, even if it's just for circuits. It'll save you a lot of time. So you can evaluate this out, plug that in however you're inclined, and we find A1 equals 2 plus j 1.15, and we can find A2 equals 2 minus j 1.15. And lo and behold, that's an interesting phenomenon. What can we say about those two numbers? They are also complex conjugate pairs. So as luck would have it, well, it's not luck, it's math, so science if you're inclined. When we do complex numbers, if we have a complex whole, if that's A1, P1 is complex, meaning it's underdamped, then the second term is always A1 conjugate plus P1 conjugate, where P is some pole and A is the coefficient. So once you've found one of the coefficients, you know both the coefficients. And that will be true. So we don't have to go through and do the cover-up rule for both of them. We only need to do it for one. And then by default, we have found the complex conjugate pair, and we can take advantage of that. And this is where I don't mind. I mentioned this earlier. In the solution of this, we could take the inverse Laplace transform and we could write it out as S plus J 1.15, just to substitute in what we've already done, e to the minus 0.5 minus J 0.866 T plus S minus J 1.15. What?
S or 2.
This?
Yeah.
That's a S. A 2. Sorry, did I say? Yeah, I'm not doing well today, am I? I wrote out the right thing. Plus J 0.866 T. That would be our solution. I accept that as a solution. That's a valid representation of an exponentially decaying sinusoid. Maybe not something we can easily visualize, but that's legitimate. There is a trigonometric transform to get this in a form that's more familiar, where we would have something along the lines of a coefficient, whatever it may be, e to the minus alpha t, so minus 0.5 t, in this case, times the cosine, and our beta 1.15 t plus a phase term. There is some trigonometric transformation. I'll give that to you next week, or well, not next week, the week after. But this is valid. This is something you'll see in various solution techniques. Now that we've introduced complex numbers, it is worth going through and just kind of reminding you of how they work if you haven't used them before. So usually if I have something that's complex number, AR plus J, A imaginary, and I have a complex number that's BR, R for real, plus B imaginary. Well, A plus B, fairly straightforward. AR plus BR plus J, AI plus BI. And we can add subtraction as well, plus or minus, as the case may be. So, addition, fairly straightforward. Multiplication, maybe a little bit harder. A times B, well, then you wind up with AR plus JAI. This is why a calculator is a much better choice. So you don't have to do this by hand. Equals AR BR minus AI BI plus J AI BR plus AR BI. And so we still get a complex number. Remember, J times J is minus 1. So that comes into play there. Division may be a little bit more exciting. 1 over A. Well, here we typically take advantage of our complex conjugate rule. So before we do division, maybe I'll do something else first. A times A conjugate. That's often referred to as magnitude A squared. magnitude of A. And essentially what we're looking at is if we plot A in the real and imaginary domain, and we have a real component of A and an imaginary component of A, there's our point, A real, A imaginary. This distance here is the magnitude of A. It's the length of the line. You haven't seen that before, and that's quadratic. So when we look at 1 over A, one of the things we can do is multiply by A conjugate over A conjugate, which I hope we all agree is 1. And that just winds up being A conjugate, which we recognize as just changing the sign of the imaginary term over the magnitude squared. These are all things I kind of expect to have seen before. Has anybody not seen this before? It's all fairly familiar. A couple people haven't seen it, sort of. So we're going to use this periodically, more so in Unit 3, but again, you know, you really don't want to do this by hand. I don't want to. I do it all in MATLAB myself, but do it on your calculator. You will have to look at complex numbers, but so in the next case study, we looked at overdamped, we looked at underdamped, f of s, 4s squared plus 12s plus 8. And that gave us s plus 8, s plus 4 squared, and s plus 1. And if we do a little factoring here, this winds up being 4 s plus 2 times s plus 1 over s plus 8, s plus 4 squared, s plus 1. Then we cancel out those s plus 1s. If our system response has an s plus 1 over an s plus 1, is that mathematically allowed? Of course. And there will be cases where things like that may occur. And so those go away. We don't have to worry about those poles and zeros. So if you want, we have a 0 at -1 and a pole at -1. And effectively, as far as we're concerned, they cancel each other out. Now, we have a 0 at -2. We have a pole at -8. And we have a pole at -4. Well, what can we say about the pole at -4? It's repeated. So it's a repeated pole. In this case, it's a double pole. And that matters. So that's a double pole, or specifically double, though generally it's repeated. Well, how do we do partial fraction expansion here? This is still some A1 over S plus 8 plus an A2 over S plus 4 plus an A3 over S plus 4 squared. So we include each term of our repeated pole, in this case double, so we have a first order term and a second order term. If we had a triple pole, we'd have S plus 4 cubed, etc., etc. And so not much has changed other than we have this repeated pole, this higher order pole. How does that play out for us in terms of Laplace transforms? So if we do the inverse Laplace transform of f of s, well, this is still some a1 e to the minus 8t. That hasn't changed. This is still some a2 e to the minus 4t. That hasn't changed. We're familiar with that that expression. We've used that already a number of times. What's the inverse Laplace transform of this? Well, what do we do now? Run screaming for the hills. No. We go back to our table, and lo and behold, God gave us a formula. So that's good. Someone did. I shouldn't assume religion. So the Creator gave us a formula. So there it is. It's a square. It's hard to read, but again, you have it in front of you. We do have the inverse Laplace transform of that. So our bases are covered. And so that winds up being a3t e to the minus 4t. Neglecting that first term, which I probably shouldn't have included in the handout, what does that look like? And this time I can actually write down the right damping. It does look like a critically damped case. So when we have a repeated pole, we have a critically damped situation. Again, critically damped is kind of a magical mathematical situation, but it does give us some more math problems to solve. So here's our critically damped case with a repeated pole. All right, so let's take a few minutes. We're about on a little bit after the hour. Go stretch your legs. We haven't really looked at the circuits yet. So let's start to do that. We're going to introduce this concept called impedance. And impedance is effectively resistance. So impedance, like resistance, I mean resistance is the resistance to electrons flowing, current limiting, that type of thing. Impedance acts the same way. It's characteristic. And so if we look at a resistor, well, in the time domain, a resistor is still a resistor in the Laplace domain. So ZR, Z is impedance, equals R. So Z is used for impedance. So you'll see me use that a lot. And right now I'm going to add a little caveat. Right now I'm going to say 0 initial conditions. We'll come back to non-zero initial conditions in just a moment. In the capacitor in the time domain, in the Laplace domain, this is 1 over SC. And that's ZC. I should have written the C first. With 0 initial conditions. So we'll be a little bit more general in just a second. 0 IC. The inductor in the time domain corresponds to a ZL equals SL with 0 initial conditions. Why does that help? Well, these are impedances, and we treat impedances just like resistance. So all the resistor rules that we've used, resistors in series, resistors in parallel, we can treat impedances the same way. So if we have two impedances in series, Z1, Z2, well, the equivalent, Z equivalent equals Z1 plus Z2. So that's the beauty of using impedances, and similarly to impedances in parallel. Z1, Z2, the equivalence, Z equivalent equals Z1 in parallel with Z2, of course, and to write that out, Z1, Z2 over Z1 plus Z2, which is a fast formula we can use when there's just two components. If there's more than two components, you can't take that shortcut. You need to use the inverse relationship, of course. You could write this as 1 over z1 plus 1 over z2 to the minus 1. That actually goes first. And if you solve that out, you get that simplification. It's a handy one to be familiar with. So, how does that help us? Well, if we think about an RC circuit, oh, yeah. Can I just move it up a little bit? If we think about an RC circuit, and as I said, we're going to be fairly familiar with this. In the time domain, this is some source, the source of t. That's an R, and that's a C. We've looked at this guy a lot, so we're familiar with that. Here's the time domain circuit. Well, in the Laplace domain, what does this look like? This is still a source, but this is the Laplace transform of the source. And I'm not going to write the t because I'm running low on room. But that's the Laplace equivalent source. If it's a step function source, we know it's something over s. We've already seen that a few times. If it's an exponential source, it's something over s plus whatever the exponential term is. It's the Laplace equivalent. So if we know what our source expression is, we go to our handy-dandy table, whatever it is, find it, and that's the expression. Right now, I'll just leave this general as Vs of s. I guess I should probably use something besides s for source. So the subscript s is for source. The argument s is for s domain. Our resistor is still a resistor. And our capacitor now is 1 over SC. And again, I want to qualify, this is a 0 initial condition. Laplace domain. 0 IC. And so, well, just using this as ZR and ZC, what's the voltage across the capacitor here? Well, VC of S, this is in the S domain now, it's no longer the time domain. VC of S, what type of circuit is this? It's an RC, yeah, but backing up, more generally in Unit 1 concepts, it's a voltage divider in terms of Z's. So this is ZC over ZR plus ZC times V source of S. Maybe I'll start using V naught of S, just so we avoid some confusion. So that's a voltage divider circuit in the Laplace domain. In the time domain, we had to do all that stuff with differential equations. Lo and behold, it is now algebra as promised. And so, well, we can plug in what this is. 1 over SC, R plus 1 over SC times V source of S, which again is some known thing. Right now we're leaving it general. This is arbitrary source, but if it's a step function source, it's going to be something over S. Again, we've already said that a couple times. So, times some source. We can clean this up a little bit. We can write this as 1 over RC, which is just a number. S plus 1 over RC, V source of S. And what does that look like? Well, that looks like what we just spent the first hour studying. What are the zeros in this expression? Kind of a trick question. There are no zeros. As I said, a trick question. What are the poles here? Minus 1 over RC. And so what's our exponential argument going to be? Minus 1 over RC if we did an inverse Laplace transform on this. And sure enough, that's exactly what we saw when we did this as transient analysis in the time domain. And that's what we'll do when we come back from spring break. So here's the beauty of doing stuff in the Laplace domain. We do this as impedances. we get these fractions, we clean up this fraction, so it's a polynomial. That was why I had to clean this up. I don't want fractions in my numerators and denominator. I had to do a little multiplication, rearranging to get this as a polynomial, to find the zeros and the poles fairly easily. And then we could do partial fraction expansion, though we need to know the source before we do that. And that's something we'll visit after spring break. To be a little bit more general now, what about if we have non-zero initial conditions? So if I look at my capacitor, to clean things up a little bit, well, in the time domain, this is IC of t, and that's VC of t, right? And that's the voltage across the capacitor and the current through the capacitor. And we're not at steady state, so nothing's zero. And so we know IC of t equals CdVC by dt. Something we've seen a lot, we're familiar with. Well, I should have written this down here. IC equals CdVC by dt. This is the time domain circuit. I can take the Laplace transform of this. Right? Take the Laplace transform of both sides. What's the Laplace transform of IC of t? Well, that's just IC of s. It's some value. I mean, we could find it on the table if we had an expression, but that's the general form. So the current in the s domain is just IC of s. And likewise, we can look at the right term, the Laplace transform of C dVC by dt. Well, the c is just a constant, so we can bring that out front. That doesn't affect anything. dVC by dt. And now we take the Laplace transform of this derivative term. Well, what do we do now? How do we take the Laplace transform of that? Well, once again, we run for the hills. Or we go back to our Laplace table. And sure enough, we are given the formula. Here's the differential term. There's the Laplace equivalent. Well, that was provided for us. We're going to charge you extra for that one. And that winds up being SC VC of S minus C VC 0 minus. Just plugging in, instead of using F like we see here, where are we? Our VC. So all I'm doing is taking the Laplace transform of this, transforming it into this one. And again, that comes out of the mathematics of the Laplace transform. You don't need to necessarily know where that comes from. I can show you if you want later. But that's the Laplace equivalent. Now, this is an initial condition term. That's worth pointing out. That's an initial condition term. That's the voltage at t equals 0 minus. We've seen that a lot. So that's 0 minus, just before things get interesting. That's the voltage at t equals 0 minus. If it's 0 initial conditions, this goes away. So we can recognize 0 IC. What are we left with? IC of S equals SC VC of S. What does that look like? Maybe I should write it differently. VC of S equals 1 over SC IC of S. What does that look like? Very first equation we ever talked about. That's Ohm's law in the S domain. And lo and behold, I did not lie to you. That's ZC equals 1 over SC. V equals IR, right? So there's our 0 initial condition. That checks. To go back to what we had up here, non-zero initial condition. Well, we have IC of S equals SC VC of S minus C VC 0 minus. And if I rearrange things a little bit, I can rewrite this as VC of S equals 1 over SC, IC of S, and we now recognize that's our ZC. We've seen that a couple times already. Plus VC 0 minus over S. That was just doing a little, just to get that out of the way so we don't get confused. I was just doing a little bit of algebra rearranging, no problem. Well, this is the voltage across the capacitor, right? This is still an Ohm's law expression, and this is an initial condition. So in the S domain, what do we wind up looking at? Well, again, here's our time. So I'll write this as IC of t plus minus EC of t. There's our time domain form. And what is our equivalence then? In the S domain, we have a capacitor, 1 over SC, and we have an initial condition term, VC 0 minus over S. This is IC of S coming in. And where we want to be a little bit careful when we think about this, the voltage across the capacitor in the S domain is the voltage across both those components. So the voltage drop, Ohm's law applies, the voltage drop across the capacitor is IC times the impedance, 1 over SC, plus the initial condition term. This is the equivalent transformation. This is the Laplace domain equivalent circuit. So when we go to the Laplace domain and we draw a capacitor, we have to check for initial conditions. And so what does that mean for our RC circuit? Well, if we go back to our RC circuit, again, we have the source of T, some R, and some C. There's our time domain circuit. What does our equivalent S domain circuit look like? Well, if we don't know what the initial conditions are, this is now the source of S. The impedance of the resistance is still just R. This is 1 over SC. And there's our initial condition term. So our circuit analysis has to include this other source, this initial condition source. And so that's the equivalent circuit more generally. It's the full equivalent. If this is 0 initial conditions, well, VC 0 minus and is 0. What's a voltage source at 0? Essentially a short circuit. And we go back to the simpler case. So there's our circuit. Now the question again to come back a little bit, what is VC of S? Well, VC of S is again this. So the voltage across the capacitor is the voltage across both those components. Something you want to emphasize because it's caused some trouble in the past. It's the voltage drop across the capacitor in the S domain plus the initial condition term. In an analysis concept, how do we find this? So we can say VC of S equals voltage across ZC plus VC 0 minus over S, right? It's just a way of writing it. It's the voltage across this component plus the voltage across that component. That's that guy, and that's that guy. I'm just calling that VZC. Well, what's VZC? We haven't done this for a while, but how do we find this? How do we find just the contribution from this term? What type of circuit is that? Still a voltage divider, but a little bit more complicated voltage divider. So this is 1 over SC, which is ZC, R plus 1 over SC times what? This is where things get a little bit tricky. V source of S minus VC0 minus of S. We can do source reduction, which is essentially what this is. Now we don't know what this value is, but mostly we'll look at step functions, so these will reduce fairly well. But that's source reduction. Voltage sources in series add or subtract, depending on the polarity, of course. We haven't done that for a while. But these are voltage sources in series. We can combine them, and effectively that's what we've done here. Or if you like thinking about it, it's the voltage at this node minus the voltage at that node. That's your voltage divider. We've used that concept as well. Plus VC0 minus over S. And so that would be the expression we would analyze to find the voltage across the capacitor as a function of time. So first order circuits, transients are easier, I tend to say. You know, this looks a little uglier. It's not bad, but perhaps a little bit more work. When you look at second or higher order circuits, the Laplace domain winds up being easier. So if you had a good understanding of homework 4, maybe you're looking at this saying that's silly. And sure, I won't disagree with you too much. But this is the approach we do for first order circuits in the S domain. Likewise, let's look at inductors. So we have an inductor. Again, BL of T and an IL, and this is our time domain equivalence, or time domain circuit. And we know BL of T equals L dIL dt. Again, we've seen this a lot. We can do the same process we just looked at. Let's take the Laplace transform of this. Well, the Laplace transform of the voltage is just going to be VL of S, whatever that equivalent circuit is. We're leaving it general at the moment. And then the Laplace transform of the current is SL ILS plus our initial, or minus our initial condition term, IL 0 minus. Again, that's the same thing we just did for the capacitor. I didn't bring up the Laplace table, but we're applying the Laplace table to these expressions. And that's our form. Well, what do we have here? This is our familiar ZL. There's an Ohm's law expression and an initial condition term. But note the polarity here, and this matters. So in the Laplace domain, what do we have? Well, this is SL. We just said that a moment ago. And we have an initial condition source with the opposite polarity, LIL 0 minus. That's L times IL, just to point that out. That's inductance times the initial condition current. That's the equivalent circuit in the Laplace domain. And there's no over S here, pay attention. Laplace domain. So as we go from our time domain circuits to the Laplace domain circuits, here's our initial conditions, here's our impedances, and for the capacitor as well, the equivalent circuit. These are the things we want to make a note of. The equivalence between these two and the equivalence between these two and this guy. I know I'm moving that fast, but you have it in your notes already. So, this is what we want to look at. So, where are we? Where are we? We can go a little long today because spring break's coming. So. I think this is the second or third page of the handout. If we look at a circuit, it looks like this. So this goes back to something we've done on both homework 4 and homework 5. We have to find our initial conditions. Oops. And so L1, L2, C, we have to find our initial conditions here. How do we do that? Well, our source is 5u of t. Let's make this more interesting. Let's change up from the, since we don't have a lot of time. 5u of minus t. So what does that mean for us? This is a source that turns off at t equals 0. And so we want to find the Laplace equivalent circuit. In order to find the Laplace equivalent circuit, what do we need to find? We need to find the initial condition. So we need IL 0 minus, IL1 0 minus, IL2 0 minus, and VC 0 minus. And what are they? We'll do this kind of by inspection. At t equals 0 minus, what's the status of our inductors? They're short. What's the status of our capacitor? It's open. Why? Because it's been like that since minus infinity. Once we get to t equals 0 minus, well, that's half of infinity. That's a long time. And so we're at DC steady state. Inductors are shorted. Capacitors are open. I'm going to argue that's 0.5 milliamps downward. And that's 0.5 milliamps to the right. And that's 1 volt. Do we agree? Anybody disagree, or is anybody not sure? So where does that leave us? What's our Laplace circuit look like? Well, in the Laplace domain, what is our source? Kind of a trick question. What's our source in the Laplace domain? This is a source that turns off at t equals 0. Laplace, it's a short. Laplace solutions are only for t greater than 0. Our source is off, which is 0, so our source turns off. That's 4K. That's 2K. And this is SL, so 10 to the minus 5 S. And now we have an initial condition term, minus plus. And again, pay attention to the polarity. So minus plus, current is going downward, current is entering the minus side. That's the polarity we use for our initial condition on inductors. And we have 0.5 times 10 to the minus 5. Which we could write as 5 times 10 to the minus 6 if we want. So that's Li L1 0 minus. That's SL1. The resistor state of resistors, of course. And likewise, our other inductor, 10 to the minus 5 S, which is SL2. And again, our initial condition term happens to be the same initial condition by coincidence. 10 to the minus 5. So that's LIL2, 0 minus. and then into the 2K. And the capacitor in between here. 1 over SC, so that's 10 to the 9 over S. So just doing the inversion. And then our initial condition term, plus minus. VC 0 minus, we said was 1 volt. That's 1 over S. That comes from VC 0 minus over S. And there's our equivalent circuit. And in the Laplace domain, these are impedances. We essentially do the unit 1 material, but with S's. We have this variable S. Everybody okay?
Hold on 1 second.
I want to look at the RLC series circuit before we go. So, if we look at our RLC, we've got a couple minutes. We don't have to get packed up yet. The plane's not leaving. There's our RLC circuit. Let's do a 0 initial condition problem. So everything's nice and simple. There's R, there's L, there's C. There's some V source of T in the time domain. So what are we looking at here? Well, this is our time domain circuit. Let's look at the Laplace circuit. V source of S, whatever that Laplace transform is. There's R. There's SL. There's 1 over SC. No initial condition, so we're done. What's VC in this case? There's VC of S. Voltage across the capacitor, because we have no initial conditions. We don't have to worry about that yet. We'll do that after spring break. And if we look at this circuit, then what is VC of S? This is still a voltage divider circuit, so we can say VC of S is 1 over SC, R plus SL plus 1 over SC times V source of S, right? No problem. Well, I can do a little bit of rearranging here once again. I can rewrite this as 1 over LC. This is some fast algebraic manipulation. S squared plus R over L, S plus 1 over LC, V source of S. Right? Maybe you don't quite believe me, but you should prove to yourself that's the case. They are equivalent and fairly confident. If I take this for a moment, this winds up being n of S over d of S, right? They're polynomials. No problem, times V source of S. And let's rewrite this for a second. ds times Vc of S, the voltage across the capacitor, equals n of S times V source of S. And let's write that out. S squared plus R over LS plus 1 over LC times Vc of S equals 1 over LC times V source of S. And so all I've done is taken that voltage divider expression on our previous page, did a little bit of algebra, did it fast, so maybe you're not quite confident I didn't make a mistake, but I feel pretty good about it. Well, what about if we take the inverse Laplace transform of that? Well, what's the inverse Laplace transform of S? We didn't explicitly say it, but we saw it. S corresponds to what? D by dt. And so S squared, d2 by dt squared. So, if we take the inverse Laplace transform of this, what do we wind up with? Well, there's a d2 by dt squared plus r over L, dvc by dt. plus 1 over LC, BC equals 1 over LC, BS. This is all in the time domain now. Does that look familiar? I would say so. I took the inverse Laplace transform with this. Lo and behold, the Laplace form, this polynomial form, corresponds to differential equations.